Let's determine the Wronskian of the two given functions here, e to the power of 2x and x e to the power of 2x. The Wronskian of these functions, is the determinant of an equivalent matrix that can be formed from these two functions here. Since we have two functions, automatically the number of columns would be 2, representing both functions therein. Now, to get the determinant, of course, this should be a square matrix. In short, we only have 2 rows as well. But this could also be verified further by this process n-1, telling us the number of times we're going to derive the functions. We have 2 functions here, so we have 1. In short, we only end up on the first degree order derivative of these 2 functions. Hence, their first order derivative will comprise the second row, then it should be a 2 by 2 matrix. So let's start doing that. The first order derivative of e to the power of 2x is itself e to the power of 2x times the derivative of your exponent 2. Okay, we'll be simplifying that later, and we also need the same thing here as we are going to look into the second function, because this may need another process because this is a product of 2 functions x and e to the power of 2x. Hence, we will be using here the product rule. So that would mean x times the derivative of e to the power of 2x is itself times again 2 as the derivative of our exponent, plus the derivative of e to the power of 2x itself times the derivative of x, which is just equal to 1. This is the product rule. Take note of that. So you need to review that as well. In short, our matrix here will be e to the power of 2x, x e to the power of 2x, and then simplifying the second row, twice e to the power of 2x, and you will have here a binomial expression, twice x e to the power of 2x plus e to the power of 2x. Now we cannot combine them because this is algebraic in nature, and this is only this can be represented by 1 or a constant, so let's leave them as they are. So we have this 2 by 2 matrix, and the point now is to come up with a determinant, and the determinant of a 2 by 2 matrix is easier to remember, or you can always follow the idea of multiplying diagonals from upper left to lower right. Okay, multiplying these 2, and that would be a positive value, and subtracted with this diagonal from bottom left to upper right. So let's start with the red first, so that we will not be confused with the process. So again, this is on the Wronskian of e to the power of 2x and x e to the power of 2x. So we'll start with the red one. Take note, you're multiplying monomial to binomial, so always express the binomial in form of a parenthesis. You have e to the power of 2x times twice x e to the power of 2x plus e to the power of 2x. That's just the first diagonal. Then, for this process, so minus, as mentioned, twice e to the power of 2x times x e to the power of 2x. Okay? So, going further, simplifying them, you will have, by distributive property, twice x e to the power of 4x now. Okay, that's 4x. Because you're adding exponents of the same base, 2x, and 2x is 4x. Hence, you will have to do the next one here. The next process, you have plus e to the power of 4x. Okay, this process product. And then minus twice, you will have x e to the power of 4x as well. 2 plus 2, 2x plus 2x is 4x, and then you're multiplying 2 and x here. So with that, you can see that the first and the third will just cancel themselves. In short, the Wronskian of e to the power of 2x and x e to the power of 2x is e to the power of 4x. And if these are subjected into specific examples for the solution of non-homogeneous higher-order equations where we cannot use the previously presented tables, we are going to use a variation of parameters. We will be using the concept of the Wronskian. Okay? Thank you very much for watching.